let's now look at the second aspect of this coherence, which is the spatial coherence. But let's go back to our original definition. Again, I am looking at the correlation between the electric field at a location R1 and correlating that field with the field at a location R2, but at the same time t. That is, we are looking at two different locations R1 and R2 at a definite time t. This clearly captures the spatial aspects related to the wave, and the coherence length, L coherence, like in the previous case tau coherence, actually goes like lambda divided by the angular size of the source, where lambda is the wavelength of the light. So whether you're coming in with radio waves or you're coming with optical waves, it is going to be proportional to that lambda. So larger is the wavelength, greater is going to be the coherent size, and delta theta is the angular size of your source. Again, I'm writing down the result. We will quickly look at actual implementation and see how this comes about. If I'm looking at two spatially distinct points, I'm asking whether the fields have any relationship, phase relationship or amplitude relationship between them for two different locations, spatially distinct location, but at the same time t. So just like in the previous scenario, we looked at the idealized situation of a monochromatic wave, which is an infinite train in time. One can think of in this situation, for example, a plane wave. A plane wave is of infinite extent, right? And you have got these planes which is traveling in a particular direction k, which is the propagation vector. Now if you ask what is the correlation between the field at two separated points R1 and R2, now these 2 points obviously are going to remain correlated because it's an infinite plane wave. Even if you think of a point source, okay, an ideal point source which is emitting spherical waves, right, in all directions, even here I can ask what is the correlation between the field at one point with respect to the field at other. You will see that there is a definite relationship for a perfect point source. There is a definite relationship between the fields at these two locations. Now these are idealized situations. So how does one think about a non-ideal situation in these scenarios? So imagine I'm coming with another wave, another plane wave, which is overlapping, but it is having a different k vector. Similarly, there could be a third wave which is traveling with another k vector. So you see that every point, now there are going to be a bunch of these k's which are not necessarily talking to each other. So now you can clearly see that if I have a source which is not purely a plane wave, or if I have a source in which is not purely a point source, but it is a bunch of sources of which are uncorrelated among each other and yet are producing, you know, their own spherical waves. So the electric field at these arbitrary points is invariably going to be a combination of the fields arising out of each of these point sources, which are themselves not talking to each other, and hence that is what will effectively turn the if you think of the point source which has got angular size which is extremely narrow in comparison to a finite source where the angular size is much larger, and so on. So this notion of angular size will determine the correlation or the coherence between these 2 points. So let us see what kind of an interferometer will capture this aspect. Again, I'm looking at another interferometer, which by the way is the Young's double slit experiment, right, or the Young's interferometer. So what you have there is the following. You have a opaque screen, right, which has got two holes in it. And so this and there is an observation screen which is there, and what I have is essentially a point source which is emitting radiation. So let me call this as a point A. So I'm going to draw a ray diagram. So the light from the point source reaches the slit 1 and the slit 2. Let me call this slit 1 and the slit 2. And this radiation, because this is a point source now, it's going to combine at its symmetrically opposite point, and you see that the path difference between the path 1 taken by light and the paths taken by the light path 2, both of these, there is no relative path difference between them, hence they are going to arrive at this point in phase, right? And on this screen you are going to get basically the Young's interference fringes. So what you're going to observe is basically interference fringes of this kind on this screen. So I can calculate again the same quantity, which is visibility, which is going to be, I'm going to again look at the I max by I minimum, right? So I'm looking at I max and I minimum, I calculate my visibility, and clearly you see that I'll get very good visibility if I'm coming with one point. In the same interferometer, now I come with another point B, which is a different source in contrast to A. So the B itself would have a light reaching both the slits, and these would combine at a different location, and now you would have another fringe pattern which is related to this second path, and you see that this is shifted, the central fringe is shifted because of this, because of the location being shifted in the opposite direction on your source side, right? Clearly you see that one is where there was a minima, there is going to be a maxima from a source which is spatially removed from the original one. So now you see that one can think of the size of the source as small s. So now I can essentially, basically write down geometrically all these aspects. Imagine this angle is theta, which is the measure of that source. So now I am looking at the distance between the screen and the double slit is small d. This distance between the double slit and the source, let us call it r. The spacing between the original fringes, right? The spacing between the fringes is actually given by lambda d by L. This you can easily figure out. So from B to the point 1 minus B to the point 2, if this path difference is, let's say, delta, and if this is equal to lambda by 2, I am done, right? Why is that? Because that would basically overlap between one fringe to the other fringe. Originally I have a phase difference of lambda, right? If I create a path difference of lambda between these two paths, I get the next fringe. So here, if I create a path difference of just lambda by 2, I would be going from the maxima to the minima. Hence, the maxima of the second green beam now overlaps with the maxima of the minima of the original blue beam, right? So that is the kind of a condition that tells you how how the visibility will actually decrease, with the contrast between minima and maxima will go away. So now you see that my delta is, and the difference between the two fringes, let's say, is L, right? So you can clearly see that my path difference, this extra path traveled, is delta. So you see that my delta is given by L times theta, which is L times theta being S over R. So you will clearly see that the fringes are going to be visible if B is not significantly, or rather B is not far away from A, right? If B moves only so slightly that the fringe pattern, that the maxima doesn't overlap with the minima of the previous fringe due to A, then you are going to continue to have the fringes. So clearly there is a limit on S, and that is given by essentially lambda R by N. That is, I'm specifying this. I've ignored the factor 2. So you see that my L coherence, if you like, is going to remain coherent only if it is less than R by S. You know that my theta is S by R. So this is equal to lambda by theta. So you can think of it this way, that the field will remain correlated at these two points, right? So the fields at these 2 points are going to remain correlated only if the angular size and the wavelength is such that this constraint is maintained, right? And this is precisely what uh, is shown geometrically here. This is formally derived uh, in optics, and it's popularly known as the Van Sittered Zernike theorem. Uh, uh, this basically relates diffraction, okay, from a finite size aperture, which is akin to a source, and sees how how these correlations last beyond as the field propagates. Now, I want to emphasize one very important difference between the spatial and temporal coherence, and that is the following: that my temporal coherence is limited by the bandwidth, the spectral bandwidth of the light, whereas my spatial coherence is limited by the angular size of the source. Now you see clearly, if my source is fixed and I'm just watching the light coming to me, the bandwidth remains more or less fixed for a stationary source. But as I go further away from a source, you will see that my size, the apparent angular size of the source from my observation point, is going to decrease as I go further and further away, right? So for example, we are looking at the sun and the moon. They look of equal size. That is simply because the moon is much more closer to us than the sun. Whereas if you look at the stars, which could be a star similar to the sun that appears like a point, so you see that the spatial coherence characteristics of sunlight in comparison to starlight are going to be distinctly different. So as you go further and further away, the light becomes more and more spatially coherent. So I will give you a few exercises for you to estimate these numbers, and that will help you understand these ideas in a more physical and a concrete way. Another very important note which I want to emphasize is the fact that you can clearly see that one aspect of coherence relates to its temporal coherence, which relates to its bandwidth. The other spatial coherence aspect relates to is finite size and the wavelength. None of these are essentially the characteristics of a laser. In a laser, you do have a narrow bandwidth, but you could have had such a bandwidth by putting appropriate spectral filters that pick up only a narrow that allow, for example, only a narrow spectrum of light. Or in other situation, you could have the laser does have a very small angular size, but you can take a normal light and confine it in such a manner that it also has an extremely small angular size. So there is nothing that specially targets the laser. So these coherence aspects indeed can be achieved better and better even through thermal sources, and these are not what distinguishes a laser from a thermal source. So the real distinction of the laser from the thermal source arises from higher order correlations. Okay, that is something that I will not talk about, but I will probably just indicate to you in a simple slide. But there what you're going to do is you're going to look at the intensity correlations at R1 T1 and intensity correlated to the intensity at R2 T2. So these are no longer the electric field, but now mod squares of the electric field. That is, you're looking at now higher order correlations between fields, and it is this that distinguishes a laser from another thermal source. So this aspect actually captures the statistics of the light that is coming in, and we are not going to deal with this because this is not a quantum optics course, but it's sufficient to mention that what you get is a Poisson distribution of photons, of the statistics of the photons that come out through a laser, whereas if you look at a thermal source, what you will get is a thermal distribution, which is different from the Poissonian distribution. So in terms of quantum optics, you can think of it in terms of randomly arriving photons in comparison to a thermal source in which the photon comes in bunches. So there is a bunching of photons for a thermal source, whereas for a laser source, it is random arrival of photons. So this is beyond this course, but that is some point that we need to emphasize just for the sake of completeness. Thank you.